Hi everyone, let's go ahead and get started with deep learning tutorial with TensorFlow. In this lesson, we will be seeing how you can get started with computer vision with deep learning. We will be using Fashion MNIST data. In Fashion MNIST data, we have 10 classes and these 10 classes are mostly based on the fashion items like we have sandals, boots, t-shirts, pullovers, all these. So before that we need to understand that what is the computer vision and how these deep learning neural networks are used in computer visions. Well, so computer vision is a field of the study where machine learnings are used to interpret and identify context on given image like a human does. It enables the machine learning to process and analyze images and videos. It makes it possible to understand for computers its content and context based on the visual data. For example, you can see here in this example, we are given with so many images, or you can say the machine learning is given these so many images, and then machine learning need to understand or need to identify these distinct images there. So we are seeing here a deep neural network. These deep neural networks are fully connected neural network. First layers are known as the input layer, and then the intermediate layers are known as the hidden layers, and then we have there the output layer. Although in this image it is being shown that these 4 layers are the input layer, it's not true. The first layer is only the input layer, and other than that is considered as the hidden layer, including these layers and these layers, these layers and these layers. So the final layer is considered as the output layer, and other than these two input and output layers, all these layers are considered as the hidden layer. In machine learning, these images are fed in input layer, and then the data of these images move forward from this input layer to the output layer. So this is known as a forward neural network, or you can say the feed forward neural network, where data or information passes from backward to the forward. In the process of the tuning your machine learning model or deep neural network, other information is passed from forward to backward, that is known as the back propagation. Some of these things I have already covered in my previous videos, and in coming lectures I'll be also covering these things in a little bit more detail. Let's go ahead and see how these images are identified in machine learning term. Based on these images, some of these features are identified as these information goes forward in your neural network. At the earlier stage of your neural network, small features or local features are identified, like here you can see, and as it goes forward, more complex features are identified there, and then finally a classification is done at the last stage. With these intermediate stage, you can see small features are identified here, and a little bit more face features, like here it is identifying eyes, nose, ears, mouth, lips. All these are identified in intermediate stage, and as your data forwards in neural network, at the last stage or about to last stage, overall this whole context is identified, like this whole image context is identified at the last stage there. Here are 5-step explanation of the computer vision. We have to do image acquisition. That means you need to capture the visual information, you need to get the images, videos. For example, you want to work on computer vision project, you need to identify your problem statement, and then for that problem statement you need to acquire the images. So this is known as image acquisition. There are multiple ways to acquire the images. The one way, if images are already present somewhere, then you can filter out the images which you want to get. Otherwise, if you want to take the open source images, you can extract, or you can scrap the images from the website, by keeping in mind that images should not be the copyright by some other third party. Other than that, you can also prepare your data set by clicking images by yourself, by taking photographs by yourself. For example, let's say if you want to classify two types of the plant, then you can take the images, multiple images of those two types of the plant, and then you can prepare your data set. The next step in computer vision image processing is image pre-processing. Once you have got your raw images, then you need to make sure that your images are in proper size, resizing is done, normalization and removing the noise from the images are done properly. Thereafter, in third stage, feature extraction happens. Nowadays, in deep learning, feature extraction is done automatically in intermediate stage. So this feature extraction happens automatically in deep learning. Then this final classification happens at the last stage. So moreover, 3 and 4th step, these you can combine together. And then the final step comes there, the object recognition or image understanding. So in fact, these 3 steps are involved here in classification of these images using the deep learning, where the feature extraction and the image understanding, all these things are done in this single step process there. Let's go ahead and try to understand these image feature extraction in a little bit more detail. We have here colored image of a dog there, just for our understanding, although we are going to work on fashion MNIST data. But just to understand that how image feature extraction is done, I am taking here a dog image. So this dog image is there. Generally in computer vision, images are represented in the form of red, green and blue layers. So it is known as the RGB channels. So there you have these dog features. Suppose that this is represented in these 3 channels, red, green and blue features. So the one way to extract the features, you can convert it into a grayscale image. Other features can be like, you can take the mean values of these RGB values together. Other than that, there are many other feature extractions which are done when you apply deep learning model, like you have seen these features. Let's go ahead and list out those features. So I have here complete list of those features which are calculated internally once you apply deep learning. Your deep learning model extract lines, edges, corners, blobs, circles, rectangles, triangles, polygons, textures and other hidden patterns. So your model once extract all these features from given images, then at the multiple stage, by using the filters, these features are extracted at the multiple layers there. So I'm showing here the feature extraction at the multiple stage for this particular dog. Once it starts moving deeper and deeper, how these features are extracted there. Now you can see there at the initial stage, it has low level of the features, but as it goes deeper and deeper, it keeps it keeps detecting more complex features. So these plots are taken from the internal layers or the hidden layers. You can see in this, from these hidden layers for the dog image. So that's how these machine learning model extract these internal features. You can see from these image as well. So once your CNN or neural network focus on particular block of the image, in that particular block of image, it try to find out the orientation, blobs, texture, all these things. Here it identifies that there is the the orientation, and here around these eyes there is the orientation. So something like that, it can represent there the edges of the dog image there. And if you go in more details, you will be getting something like these at the multiple stage there. Alright, let's come back to our original dataset which we are going to use in this lecture. We will be using Fashion MNIST dataset, and other than that we will be also using here another tool which is known as the OpenML. So we will be downloading Fashion MNIST dataset from the OpenML. This is the kind of the tool which offers all kind of the dataset. It is currently offering 5000 types of the dataset. Here I have got the Fashion MNIST dataset. If you want to find out any dataset, you can simply search those dataset here. You will be given the list of those dataset there. So I have here a Fashion MNIST dataset. You can get the description of the Fashion MNIST dataset and the available target classes. So total I have here the 10 classes: t-shirt, trouser, pullover, dress coat, sandal, t-shirt or shirt, sneaker, bag and the ankle boot. So these the 10 type of the classes available in Fashion MNIST dataset. Other than that, you can also see these Fashion MNIST dataset details at the GitHub. Here at the GitHub, you can see Fashion MNIST dataset. Here the clustering, a 3-dimensional clustering was done to show you how the similar kind of the things are the clustered together. Anyway, so this also has these labels and the features. So why these are given? In fact, in our dataset, we will be having the target labels as the 0, 1, 2, 10 till 9 numbers, but their actual labels are given here. So these things we need to prepare manually while writing the code for this. Alright, perfect. Let's go ahead and see this OpenML so that we can understand that how we can read Fashion MNIST dataset from the OpenML. Alright, so it has there the documentation. You can click on the documentation and then you can click on the get started, and then you need to just zoom in so that you can see it properly here. It has there the thousands of the dataset. It has the models and the pipelines, extensive APIs. If I click on the extensive APIs, I'll be getting here. You need to install first OpenML with the pip install OpenML. Thereafter, you can list out the datasets. You can also read the dataset, something like this: openml.dataset.get dataset, and then you give the name of the dataset which you want to read. Other than that, you can also break these dataset with the OpenML, but we will not be breaking these dataset here. We will be using OpenML just to download the dataset from there, that's all. Although OpenML offers so many other features, like you can use machine learning with the OpenML as well, but we are very much comfortable of using machine learning with scikit-learn, so I don't think to make it complex using the OpenML. So the use of the OpenML will be only to download the dataset from here. Alright, so let's go ahead and see this dataset. Now in this dataset we have total 10,000 examples which will be used to test our model. 60,000 examples will be used for the training, and each of these images are 28 cross 28 pixels, and these are the grayscale images. That means it's just a single channel image. And then we have their total 10 labels. Now you can see there, these are the 10 labels for these images. We have t-shirts, trousers, pullover, dress coat, sandal, shirt, sneaker, bag and the ankle boot there. Alright, let's go ahead and read this dataset using the OpenML. But earlier, as I told you, that you need to install first OpenML. Thereafter you can read the dataset. So I'm just gonna uncomment this one, but before that let me tell you one thing. If you are using heavy the processing, then you should change your runtime to the GPU. Since it is a small neural network, I do not need GPU, so I'm not gonna use GPU for my the tutorial here. So I'm just gonna install here OpenML, pip install OpenML. If you are using Jupyter Notebook or Google Colab, then you need to put their exclamation mark to install your Python packages there. So it has now installed this OpenML here, you can see, and other related dependent packages are also installed here. All right. So the OpenML has installed. I'm also I have also provided here a link which you can visit to see the example how you can use the OpenML examples to extract the data set. Alright, so this is the example to extract the data set. Other than this, you can also use the scikit-learn OpenML data set extraction as well. So you can say that here scikit-learn OpenML. Alright, sorry. Here you can say something like that. scikit-learn.datasets, there you have the fetch OpenML. In this you can provide some of these things, some of these parameters to also download the data set there. So any of these way you can use to download your data set. So we will be using here a dataset fashion MNIST dataset. This is already installed, so now I don't need to keep install that one. Let's go ahead and hide this one. All right, add additional cell here, and then from OpenML dot datasets import get underscore dataset. All right, so we have got here from OpenML dot datasets import get dataset. So with this we can import our dataset. But before that, we need to also import here some of the few common libraries, like import matplotlib.pyplot as plt, import scikit-learn. In fact, we don't need scikit-learn here. We need here import pandas as pd, import numpy as np. Alright, so these are the common libraries which we will be needing for our data pre-processing. Let's go ahead and download our data set. MNIST is equal to, in fact, fashion MNIST is equal to get underscore data set. Now, do you recall here we had an example? So like this, I need to just give the name of our fashion MNIST dataset to download that here. So something like this. Let's go ahead and run this. Depending on the dataset size, it will take a while to download this whole dataset. Alright, so dataset is downloaded. Now we are having here fashion MNIST. Let's see this fashion MNIST. Sorry, the spelling was wrong. So in this fashion MNIST, total number of features we are having here 785. Number of instances are total 70,000, which includes training and test dataset together. Alright, once you have got your fashion MNIST dataset, then you can get the data from this dataset by typing there the get dataset, something like this. Alright. So I'm just gonna copy that whole thing from there, and then I'm gonna just paste it here. In fact, this is fashion MNIST. So I write here the fashion MNIST dot get data. Now I should be able to get the data in our X and Y variable there. If you check this X, you will be getting here the pixel size of these images, the fashion images. Alright, so these are the images. These images size are 28 cross 28. So here we are having these for each pixels data there. If you multiply that 28 cross 28, you will be getting the total number of the columns there, so that you can get with the x dot shape there. So total 785 are there. All right, and if you check the last column here, so the last column is class there, and if you check here the y, So y is empty because here I have given dataset format is equal to the data frame. If I don't give it, then in that case I should be able to get here the y. Okay, even in that case y is not getting there. So this whole x is there. So on this last column, other than this last column, everything is actually its input column there. Input variables are input features, you can say that. All right. So this is the one way to read this fashion MNIST dataset. Let's go ahead and see how you can download it using the scikit-learn. So from sklearn dot datasets import fetch ml, fetch OpenML. So this is package which we are gonna use. This is method actually which we are gonna use to download the dataset. Now I write again here MNIST underscore fashion is equal to fetch underscore OpenML fashion MNIST there, and then I say here the cache is equal to the true. That means if it is downloaded already, it will not download it again. So this fashion MNIST is the dataset name there. It will take again while to download this whole dataset there. All right. Well, waiting for some time to download it. Once it is downloaded, then you can analyze your dataset. So you can write here MNIST underscore fashion dot keys. You will get to know that what are the keys available to your dataset. So it says that you have data, target, frame, categories, feature names, target names, description, details, and the URL. So URL says that the source from where you have got this MNIST dataset. Alright, so you write here MNIST underscore fashion, and then you write here the data. Now in this data you will be getting here 784 columns, because if you multiply 28 by 28, it will give you 784. Because this fashion MNIST dataset, each image size is 28 cross 28 pixels there. Other than this data, then you have here the target, that's the target variable or the target class. So this target class, their total categories are 0 to 9. This is categorical value. Other than this, you can also see frame. Since we are not downloading this as a data frame, even though after that you will be able to get it as the data frame. Do you remember when we were using our OpenML the package directly, we were getting similar kind of the data set where input feature and the target outputs were combined together. So if you use here a frame, then you will get the data frame where the input and the outputs are combined as the single data frame. If you go on the categories, so in the categories seems like this is none and it's empty. In the feature name you will be getting here all the features. So there are total 784 features there. The target name columns are their class, that's the target name column. You can also see here the description. So this is a description. All right, you can use here the print to print it properly. This is the dataset description. So it says that we have the 10 classes. Now these 10 classes we need to make this manually so that we can identify our fashion MNIST the items with these labels there. Other than that, you can see the details and the URLs. For example, I write here MNIST underscore fashion. Like URL, so it again give us the URL. This is the ID number, data ID number. This is whole URL for the dataset which we downloaded from the OpenML, and then with the details you can also see this whole thing of this dataset, like who contributed this dataset and from where this dataset is actually coming, and if you want to use this dataset as the citation, then how you can use this dataset as the citation there. All these things are available with the details there. All right, and then this MNIST underscore fashion URL, which I had already shown you earlier, that gives us the source from where we got this dataset from the OpenML. Seems like everything is clear. Now let's go ahead and read our input feature in X variable. So I write here X is equal to MNIST underscore fashion. In in that I write here the data, and then we have here Y MNIST underscore fashion. Then we have here the target. All right, you can check the shape of X. You will get here the 784, and shape of Y. So the shape of Y, this is kind of a single value. So those are number of rows there. For each row, input feature have 784, because each of these images are actually converted as the pixel values there. So it's kind of the one-dimensional data. So that two-dimensional image data is converted as the single-dimensional data, so that we can work with the numerical data directly. In the coming lectures, in some other lecture, I'll show you how you can read these images directly as the image instead as the data. So there I'll be teaching you how you can convert these image as the numerical data. All right, let's go ahead and prepare the class names. So there I have here classes is equal to, if you remember earlier we saw that t-shirt, top, trouser, pullover, all these we need to prepare here manually. So I prepare it here as the t-shirt, and then I write here as the trouser. Thereafter we have here pullover, and then we have here dress. Thereafter we have here as coat. Thereafter we have here sandal. All right, and then we have here shirt. All right, we have there sneaker, and then finally we have here bag. Ankle boot. All right, so these are the classes which we have here, and based on these index value we can select any of these classes. So we will be training our data set based on these index values target variable, which is stored here in the Y, and then during the prediction we will get the classes, actual classes or human readable classes there. All right, let's go ahead and visualize our image. As I told you earlier that these images are converted into 784 pixels there. So this is kind of the one-dimensional vector. Now I want to visualize some of these images to see that whether these vectors are actually image or what it is. Just to verify this, we need to plot, or we need to visualize each of these images with the 2x5 grid there. All right, visualize with 2x5 grid there. All right, so before visualizing this, I need to set here some parameters so that we can see our image in high quality figure. So I write here the plt.rc params. So this will make sure that our figure is high quality figure. So I write here the fig size. This is kind of the default value which will be followed in this notebook. Then I write here the plt.rc params, and then I write here the figure dot dpi is equal to 100. Alright, so this is kind of the default parameter setup for matplotlib, where we set default figure size 5 cross 5, and these are 5 cross 5 inches actually, and then we have here the dot per inch figure quality as the 100. Once all these things are done, now I'm gonna get here the default values there. So y dot unique. Now what I'm gonna get here, I'm gonna get the default values, or you can say that I'm gonna plot each of these classes here. So obviously I say there y dot unique, so I'll be getting here the 10 classes maximum. Now if you check there these digits, you will be getting it as a class 0 to 9 there. So these are the unique classes. Now I'm gonna actually plot these unique classes there. Alright, and I'm also gonna sort it so that I can plot it from the starting. So I do something like this. Alright, it doesn't work in that way. I need to do it here, and then if you see, this will be sorted as 0 to 9. Okay, seems like this categorical object has no sort value. Alright, just a second. Alright. Okay, so these categorical values don't have any sort values. That's okay, because seems like these values are actually represented as the categorical value. That's why we are not getting it as the sort value. So we need to convert it into the integer. So I write here the int x. I'm going to use here list comprehension technique. So for x in digits. So how this list comprehension technique works, it is going to iterate over digit, and then I convert these string values or categorical values in integer value, and then I get it something like this. It is just for the conversion. Alright, I mean it is just for the representation, not anything else here. Alright, perfect. So if I do it something like this, now you get it like that, and thereafter I just sort it. So once I sort it, now I'll be able, I should be able to get these digits as sorted value. So I'll be plotting here 0 to 9. That means it will be plotting us there the t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, and the ankle boot, something like that. Alright, now I need to iterate over these digits so that we can properly see our image there. Alright, I mean so that we can see each of these unique images which are stored in our data frame. So I write here for I in digits. Alright, these are the digits there. In fact, these are the unique classes there. I'm just saying that it as the digit there. Thereafter I write here the plt dot subplot 2 cross 5. That means I'm gonna plot 10 images, these 10 images into 2 rows and 5 columns there. Alright, you can put this quote here so that you can understand that I'm gonna plot these in a single row and these in a second row. Once this thing happen, then I write here the plt dot imso, that's the image show. I need to filter out all these images from the x there. Do you see there this x value? And there are total 784 columns are there. Alright, so I need to first get out the index there. So which index value I want to show as the image. Alright, so I need to get y, where this y is actually these as the categorical value there. So I need to get where this digit is equal to this I equal to y. That means if I say something like that equal to 0, it will tell us everything false because this is categorical value. So I need to do it something like that. If you remember, second and the third value were 0, that is why it is true there. So I need to get the first of these index out of these. Alright, so first of these index, so you can write it something like this, x y equal to 0. So you will be getting all those x where y is equal to 0. So there are 7,000 rows in x data where we have y equal to 0. That means there are 7,000 data available for the t-shirt there. And if I write here I log 0, then in that case I'll be getting here just a single row. Then this single row you can process ahead. So this is now coming as series. Now we need to convert it as a numpy array. So I write here 2 numpy. Now it becomes here a numpy array. Thereafter I need to reshape it to our image size. So our image was 28 cross 28. Now I get it as the 28 cross 28 as the image size. Once all these things are done, then we can plot this. All right. So that I'm going to put here in IMSO. Now one thing here, we need to convert this to equal to I, because this I is unique digit, but do remember these are integer value. So I need to convert it as the str there. So str I log 0 to numpy reshape. So it will show their image, and then I write here the plt dot title. For each of these images I am gonna get here from the classes equal to I. From classes I, that's mean from the index I. Let's go ahead and run it. Now you should be able to see there 5 cross 5. Seems like some error is coming there. Says subplot takes 1 or 3 positional arguments, but 2 were given only. So why this happens? Because 2 cross 5 is our subplot type. Now we need to also tell our subplot that which subplot we want here. So we want here I plus 1, because I starts with 0, but subplot nomenclature doesn't start with 0. So I need to tell it I plus 1, that means start with 1. Once this is plotted, I'll tell you here. So I plus 1, it starts from here. This is 0, 1, this is 1, 2, 3, but I start with 0. So 0 plus 1 is 1, 2, 3, like that it runs there. Let's go ahead and I need to also, bring it here down so that we can see it properly. The image size is 5 cross 5. I need to make sure that it is, a larger image. Thereafter, there are some overlaps. I need to remove those overlaps as well. plt dot tight layout will make sure that these overlap is removed. Once again, I need to run it. Then we need to see our figure quality. So this is figure quality. If you want to increase it a little bit more, you can put it here 200, and you can just reduce it to like just 15 cross 4. You should be able to see now high resolution image here. So we are able to see here high resolution image for all the classes. We have seen for t-shirt, trouser, pullover, dress and coat. We are also seeing here for sandal, t-shirt, sneaker, bag and the ankle boot there. So that's how you can visualize your images. Now we have understood our data properly. Now we are very much sure that how our data set are there. So these images, which are size of 28 cross 28, got converted into a single dimensional array which has size of 784. So we need to build our neural network for this image, for these images, to classify each of these classes. So currently these classes are named as 0 to 9. Later on for the prediction, we will be using something like this, where we can use human readable classes. Let's go ahead and try to understand that how you can design your neural network. So in a neural network, these are input layer, here these are hidden layer, and then finally we have here output layer. So in case of the 10 classes, you need to have there the 10 output layer. And in that case, you have to also have there the softmax activation function at the last layer. Alright, but before that we need to train test split our dataset as a train dataset and the test dataset. Thereafter we can start building the neural network. So to split our dataset, we need to import train test split from the scikit-learn. So I write here from scikit-learn dot model selection import train test split, something like this. Once this is done, alright, something like this. Once this is done, then you start with writing here x underscore train, x underscore test, y underscore train, y underscore test is equal to the train test split. You have here x and y. So it takes x data and the target data. But do remember our x data is varying from 0 to 255. But we need to make sure that we normalize our data. So we are going to divide our data with 255 so that we can normalize our data in between 0 to 1 there. Thereafter, we have here test size is equal to 0.2. That means training set will compose 80% of whole data and test size will compose rest of the data. Then I set here the random state is equal to 42. Just random state, you can select any number. If you select random state is equal to the 42, so you will get the exactly the same split as I am gonna get here. Once I get here the train test split, you can check the shape of these data set there. Something like this. So in the train data set, we are gonna get here 56,000 rows, and in test data set, we are gonna get here the 42,000 rows. Alright, other than that, you can also provide here stratify. So stratify will make sure that your data set is actually broken down as per the distribution of the y classes. So same amount of the distribution will be broken into the train and the test data set. So this also makes sure that you deal with the imbalanced data set splitting. Once all these things are done, now we are ready to build our neural network model. So we are gonna build here a very simple neural network model just to understand that how we can apply our neural network model for computer vision applications. In coming lectures, I'll be also talking about the convolutional neural network and some other neural network projects for image processing where we will be using more sophisticated code. Let's go ahead and start building our machine learning models here. So I'm going to import here, import TensorFlow as TF. Do remember I'm using here Google Colab. If you are using it on local computer, then you need to install the TensorFlow. Alright, from the TensorFlow, I need to import dense, flat and some other sequential layers as well. So I write here from TensorFlow dot keras dot layers import dense flatten from TensorFlow dot keras dot models import sequential. So you see there what happens here. I import TensorFlow. TensorFlow is deep learning library. I also import here dense layer, flatten layer and sequential layer. So let me tell you, these are actually the dense layers and the sequential layer is kind of just the functional API which combines all these layers together in kind of a single container. So the sequential is kind of the container, or you can say that the functional API which takes all these layers together and combine these layers together. and then we have here a flatten layer. So the last layer, just before the last layer, generally we add the flatten layer, which actually flat our neurons. These multi-dimensional neurons get flattened into just a single dimensional neurons. Once you have imported all the necessary deep learning libraries, deep learning methods, you can get started with building the neural network model. So I'm going to say here model is equal to sequential. As I told you, sequential is kind of just the functional API which is acting as the container there. So thereafter I write here the model dot add. In that I need to add here a flatten layer. So whatever these images are going there, be it one dimensional or two dimensional, it's gonna flat it as the single dimensional image. So I'm gonna add here this flatten layer here. Inside this I write here the flatten. Thereafter in this flatten layer I use here input shape. So the input shape I'm gonna use what I used for our X data, that's the original data. So the same shape I'm gonna use here. If you remember, the original data shape was 70,000 cross 784. This was the shape there, 70,000 cross 784. So that 784 data we are gonna use as its a shape there. Alright, the input shape for our flatten layer. So whatever we get there, this will be flattened there as the 784 values there are kind of the vectors there. And this comma also makes sure that if this value is more than that, then it will just make sure that it break down into a multiple rows, but that doesn't happen. So this is kind of just assigning a single dimensional vectors or single dimensional array there. Thereafter I write here again model dot add. After the flatten layer I'm gonna add here the dense layer. Inside this dense layer I'm gonna add here 64 neurons there, 64 cells I'm gonna add here. After this dense layer I use here the activation is equal to ReLU. Alright, so I use here activation is equal to the ReLU. So this activation function will be used as the ReLU activation function, and there are 64 cells are there. Then I use here model dot add. I use here again a dense layer of 128, and then activation is also being used here, a ReLU activation function there. After doing all these, we have here model dot add. Then we have here a dense layer. Thereafter we have here the 10 classes. Alright, so this is going to be the output class there. Alright, then we have here the activation is equal to softmax. Let me explain you once again how this works there. So this sequential layer is kind of the container which is containing all these layers in a sequence, where flatten layer comes first, then these dense layer comes, these two dense layer, which is also known as the hidden layer, and this one is used as the output layer. That's the target there. There are 10 target, that is why we used here 10. That is why we used here total 10 nodes there at the output. And the activation function softmax we used because it's not the binary. In case of the binary we use the sigmoid, but if it is more than 2 classes then we use the softmax there. Alright, once all these things are done, we can build it as the model, where we say that def, we can build it as the API or as the method get model, and then I can say that here the return this model. Let's go ahead and run it, and then I see here model is equal to get underscore model. Alright, so this model says that tuple object has no attribute as the shape. I need to see that where it is actually creating the problem. Seems like it is creating a problem at this particular stage. So it says that, okay, so seems like here I misspelled it actually. So this should be correct now. Run it once again. Oh, this one is also wrong. I'm sorry. There are the multiple times I provided there the shape. Now it should be okay. Oops, sorry. Alright, so now I have got here this model. Let's go ahead and try to understand that how this model is actually built there. If I write here model.summary, it's gonna give us the summary of this model, how these model parameters are there. Alright, how these model parameters are also calculated, we can see that. But before that, you can see we used the flatten layer, we used here the dense layer, we also used here another dense layer, and then this is the final dense layer. So the first layer output was 784, the second layer output was the 64 because we used here just the 64, and then the dense one, that means the second dense layer output was 128, and then final layer output was there the 10 there only. Total number of parameters are here the 59,850, and total trainable parameters are also equally there. Total non-trainable parameters are 0 there. Just I mean to say that there is no non-trainable parameters here. Let's go ahead and see how these parameters are calculated. So you see in a neural network what happens, this number of input parameters are going to these dense layer, those many number of the weights will be there, and for each of these cell it will also add there some bias term. So these number of parameters you can get there like 784 cross 64. Alright, because these are fully connected, so these are connected to each other. Like here you see, you can see the 784 input layers are there, and then the 64 is this layer. So the connections will be the 784 multiplied by the 64, and there are some other parameter which are added as the bias term for these input parameters, for these hidden layers. So it is calculated like 784 multiplied by 64 and then plus 64. So this says that these many number of the parameters are at this stage, and then the similarly 64 multiplied by 128 plus 128, that is here 8320 parameters, and then in the final stage it comes as 128 multiplied by 10 and then plus 10. It's something like that. If you run it, now you see the total number of the trainable parameters are exactly matching what we are seeing here. So we have got our model here. There are multiple layers are there. These are the inside layers. You can also get these layers by typing here the model dot layers. So I write here the model dot layers. If I run it, you will see there are 4 layers. That 4 layers we see there. This is the input layer, this is the output layer, these two are the hidden layers there. You can also get the name of these layers, although the name of these layers are already presented here. But if you want to just see the name of any of these layers, you can simply get it by typing model dot layers. You select the layer which you want there. For the first layer, suppose that it says there it is as a flattened layer. For second layer, it's gonna give us as the dense layer, and for third layer it is gonna give us the dense one layer. That's how you can get the layer. When a neural network is initialized, it also initializes random weights inside that. So we need to also understand that if you need to understand, or if you need to see those initial weights, you can also see those initial and the bias weights as well. For example, if we see it for the first layer, then I write here the model dot layers, and this is the first layer, and then I write here the get weights here. It's something like this. So for the first layer, I'm gonna get here the 0 weight, because in the first layer we don't have any weight there. Alright, for the second layer, if I write here 1, that means the second dense layer, we need to get the weight. So why we don't have any weight for the first layer? Because it's a flattened layer only. Its task is only to flat the vector. So that is why there is no weight for the first layer. For second layer, these are the weights here, but these weights are randomly initialized. Once model training is done, thereafter if we will compare, we will see there these weights will change there. Alright, these weights will not stay same as we are seeing here. Alright, I'm just gonna write here just for our weight 1, just for our reference, so that the later we can refer this weight 1 when we need it at the last stage. Alright, if you check here weight 1 shape, you will get here this weight 1 shape is, sorry, this is the list actually. So this weight 1 is represented as the weight and the bias term. So the first term is the weight, so weight 0 is the weight, and second term is actually the bias there. Now you see the difference there in between this and this. That's how you will understand that how I calculated the total number of parameters. So weight, total number of weight, that's mean total number of parameters. So there we have 784 cross 64 matrix. That means total values are 784 cross 64. That's what we did there. Thereafter, there are additional parameters, a small number of parameters which are considered as the bias. Initially, it is 0 before training, but after training, it may get changed there. And those number of bias are 64 because there are 64 neural cells are there in our model. This is the 64 neural cells are there. That is why we are having here a 64 bias term there. Once you have your model, now you are ready to train your model, but before that training, you need to compile your model. So, model dot compile. In this, I'm gonna use here optimizer. Alright, so a default optimizer I'm gonna use here as the Adam optimizer. This Adam optimizer is stochastic gradient optimizer, and this type of optimizer makes sure that your training happens fast, and there are high chances that you will get the best accuracy. That means in your loss function or loss method, you will get the minimum output. So minimum loss means maximum accuracy. So this type of optimizers make sure that you get the minimum loss and the maximum accuracy. So loss method which we are going to use here, I'm going to use here sparse categorical cross entropy. So why we are going to use this one, sparse categorical cross entropy? The way we have our y variable, in that case we have to use here our sparse categorical, because if you check here your y train, so this y train data is having like here these categorical values there here. So in that case, if it is like that, then you have to use here sparse categorical cross entropy. And if these values are kind of the one hot encoded, then you need to use there the categorical cross entropy. So there is just a single column, all these values are mentioned there. That means we need to use here sparse categorical cross entropy. And the metrics on which our model evaluation will happen, I'm going to use here the accuracy. That's the matrix. That is the metrics on which our model performance will be evaluated during the training. Let's go ahead and start the training. I write here model.fit x underscore train, y underscore train, and the total number of the epochs, I'm gonna train it for the 10 epochs. And then I write here model dot evaluate. So the model performance on the test data set will be also evaluated during the same time. So y test, let's go ahead and run it. Thereafter we may need to wait for some time to finish our model evaluation and the training, but seems like some error is there, and it says that sparse categorical cross entropy cast string to int4 is int64 is not supported. So seems like some error is there. I just need to see that what error is this. I just need to debug this. Wait for a second. Okay, so I just understood that this error is coming because our y was the categorical value there. So we need to just go back here. We need to do our train test split once again. But before that, we need to make sure that we convert the data type of our y. So I write here y dot as type is equal to the integer. So in this case, if you check now y, it will be converted as the integer. Now we are gonna just do here one more time so that our y train and y test also get converted as the integer. Thereafter you don't need to run all these. If you run it, there is no problem, but there is no use to run that. There is no benefit because this data is throwing error here, y train. So now this y train has been converted into integer from the string value. Now you can run your model. It should start evaluating there. So starting model accuracy starts from the 82 and it reaches here 86 and then 87. Seems like it is doing here fast evaluation. We have reached almost the 90% of the accuracy for our model. But after evaluation, we will know actually whether our model overfits or this is working properly. Alright, so the model training is done. Let's go ahead and see what is the output. So the output accuracy, it is saying that we have got almost the 88%. So seems like this model evaluation works perfectly. There is no issue with the, I mean there is small issue for overfit but not the huge issue. So seems like overall accuracy is coming around the 90% based on the given model which we have just built here, a 4 layer of the models. Seems like it is good model where we get the 90% of the accuracy. So overall you have understood that how you can build a neural network. Let's go ahead and then see how you can do the prediction based on your models there, based on your model and the given input data. So to understand the performance of your model, I'm gonna just plot a similar kind of the plot what we did earlier to show you. I'm just gonna copy this whole thing from there and then I'm gonna just paste it here so that I can show you here. Alright, this is useless. We don't need that one. Alright, so currently these digits was like 0, 1, 2, 3, something like that. And then similarly, these digits were actually given, these digits were taken as the 0, 1, 2, 3, 10 and till 9 actually, it was not the 10. Everything is same, seems like nothing is changed here. I just need to first get our the data for which we want the prediction. So I write here the test data. The test data is this one. This is the whole test data which we actually need for our prediction. Otherwise I can just take this whole thing from here and then I can write it here. And other than that, we will be using it on the x underscore test. So I write here x underscore test here. Now if you check here x underscore test, so on this data we are gonna predict our model performance, we are gonna evaluate the model performance on the test data. If I run it now, I should be able to see the test data output. Seems like something is wrong here. Just a second, let me check it. All right, let me just build it one more time. So I have here x underscore test data. Then I'm gonna just do the prediction for okay, this is something like this. Wait, what this error is saying, I need to see. This error is coming somewhere here, and this says that something is going wrong. Let me just check it here. If I have something like this where I assume that I is 0 and I run it, so I get it something like that. In that case, if I just remove it from here, okay, so the problem is here, this test data y. Okay, so the problem is, if you remember, in between I converted that y value as the integer, and here I'm comparing with the string, so I need to convert again and again, and then I need to just compare it with the integer of y. And now if I run it, so you should be able to see here the same thing what we had seen earlier, but now these classes which we are seeing from here, this we are going to get from the predicted value there. All right, so to get the predicted value, we have our model. All right, do you see there? We have our model. In this model, you need to write here model dot predict. In this I write here test. So the test is the data which we are gonna use to for the prediction. I'm sorry, in fact this reshape should go here, and if I run it again, it will run, and the test shape should be, I think I need to reshape this test one more time, because the problem is with the test data set, it's like something like this. And one more problem I'm getting here, I need to make sure that it goes inside a list there. Okay, all right, so for single value prediction, you need to reshape your test data to test.reshape 784 1 cross 784. Since we are going to predict just a single image, in that case we have to tell that it is just a single image, the shape of single image. There are 784 columns there. Thereafter we need to also put there the comma so that it becomes there a 3-dimensional vector, but actually it's a 2-dimensional vector. But in that 2-dimensional vector there is just one vector. All right, in 2-dimensional array there is just one vector which contains 784 values. It's something like this. So it does there the prediction, whatever the value it is, it predicts the probability of each of these index there. So we need to get there the max argument there. So I write here the pred is equal to the something like that, and then I write here np dot arg max, and inside that I pass here pred. So if I do something like that, I'll be getting here one more thing there. If you see there this pred, once again, this is kind of the 2-dimensional array, right? So I need to make sure that I get here, prediction for the first image, something like that. So I do something like this. In this case, I get the max index is 9. So I write here the idx is equal to the 9. Now if you want to know the class name, all right, the pred class, you can say classes. If you remember, there were 10 classes. Out of those 10 classes, I need to get here the idx, that's the index value there. So that's the idx there, the 9 idx, that's mean this last class there. And if I run it here, that's the pred class. Now if you see, you will get here the ankle boot. Let's go ahead and apply this into our model. So that I apply it here. After this I'm just gonna do the prediction. Alright, so I do here this prediction on the test data, this test data which I get it from here. That's the single image data. Thereafter, I call here np.argmax pred0 and then the predicted class. So in this, I say here original is this. Thereafter, I also say here the predicted, and in the predicted I say here the pred class. Let's go ahead and run it and then see what happens here. Okay, so this whole thing actually that shouldn't go like that. It's not like print. I need to add here something like this, and then I need to add it something like this. Thereafter, I need to use here string format case. All right, it's something like this. So we will be seeing here our predicted and the original class there. Now if you see what happens here, you have here the t-shirt, predicted is t-shirt, trouser, pullover. This dress got predicted as the shirt. So this dress actually got predicted as this one. You can see there. Seems like this image was not very much clear. That is why this one got wrong there. You have here the coat, predicted one is the coat. Original you have there the sandal, predicted one is the sandal. You have here the shirt. Original is shirt, but it got predicted as the pullover. Alright. And then the original is sneaker, but this got predicted as the sneaker. That's correct. Bag is bag, and the ankle boot is the ankle boot. Now you see in these two it got confused because you can see it as the clearly original is shirt, and this dress was also matching a lot with the shirt. Perhaps because of that it got predicted as the shirt, and at the same time this the pullover here. You see this shirt also seems like a pullover. That is why this shirt also got predicted as the pullover. Because our model is just 90% accurate. So there are the chances out of the 10 chances it will make a 1 time mistake. Although here it makes the 2 times mistake. But maybe for other cases it do not make that many mistakes. Alright, perfect. So this is all about in this lesson. Thanks a lot for watching this. I'll see you in next one.